Hello again. So we're going to see if we can't learn another series test today, another infinite series test today by looking at the limit comparison test. Last time we looked at the direct comparison test, okay, and today we're going to look at the limit comparison test. The direct comparison test, if you'll remember yesterday, we had to pick either a convergent series that was bigger than the one that we are trying to determine its convergence or divergence that converged, or a smaller series that diverged to be able to determine something. This one's a little bit different. As its name implies, it's going to use a limit. We've kind of used to using limits in our tests already, as we've done so with both the root test and the ratio test, and I guess to some extent the integral test as well. But today we are going to do this one's called the limit comparison test. Basically, the way the limit comparison test goes is like this. If we're trying to determine the convergence of some infinite series here, and it's probably some sort of rational polynomial, some sort of nasty algebra-looking function, okay? And we want to determine whether or not it converges or diverges. What we're going to try to do is we're going to try to pick a second function that we know it's convergent. So this is going to be something that we know. And once we determine this thing that we know, this b sub n that we know, what we'll want to do is take the limit as n goes to infinity of a sub n over b sub n. And by doing that, what we'll be able to do, hopefully, is get one of three results. Okay, this is if we do this correctly. There's obviously going to be a way to get a result that's none of these, but we'll have an answer of getting and this is an absolute value around here. We have the ability to get a positive finite value. So we get something that's not zero, basically, and is not infinite. Okay, so that says finite, whatever. That doesn't look like finite, but you can just pretend for me. And if that's the case, then whatever b sub n does, that's going to be whatever a sub n does. Okay, so if we get a positive finite value, then whatever b sub n does is also going to be what a sub n does. So, for example, if b sub n converges, then that would mean that a sub n would also converge. If b sub n diverges, then a sub n will also diverge. Okay, so whatever that sum does, then this sum will do. If we get 0, then b sub n needs to converge for me to be able to tell anything. And then if it does, then I can tell that a sub n also converges. If I get 0 and b sub n is a divergent series, then that tells me no information whatsoever. Okay? And if we get infinity, then we need not a sub n. We need b sub n to diverge. And if it diverges, then a sub n will also diverge. Okay, so if a b sub n converges, then we will get no good information from this. Alright, so this kind of sets us up to be able to try a problem. Okay, so we're back, and the first series we're going to look at is going to be the sum from 1 to infinity of 1 over 3n squared minus 4n plus 5. Okay, so this is the series we're going to look at. And right now we don't know what this series does. So we need to try to think of something, and I want to think of something that I do know about. The good ones to choose are going to be p-series, because those are really easy to determine whether or not they converge or diverge. This is similar to the direct comparison test. And also, good ones to choose are things that are geometric series. So in this case, I see down here that the power of this denominator is an n squared. So actually, what I'm going to kind of try to consider is I'm thinking about 1 over n squared being the series I'd like to compare this to. I know what 1 over n, that looks like it says n sub 2, so let me change that real quick. I know what 1 over n squared does. Okay, I know that that's a p-series, and that it will actually converge. So now what I'm going to do is take the limit as n goes to infinity of the absolute value of 1 over 3n squared minus 4n plus 5, all divided by 1 over n squared. And this is going to end up being the limit as n goes to infinity of, I can multiply by the reciprocal of this fraction down here. So this is going to end up being n squared over 3n squared minus 4n plus 5 when I multiply by the reciprocal. And this is actually something we do know how to take the limit of. We've talked about how this, since these degrees are the same, this is a Betsy, right? And we can look at the coefficient, so that as this thing goes out to infinity, as my n's get very, very large, this thing will trend to 1/3. And since this gave me a finite positive number, that means that I know that a sub n, okay, a sub n, this function here, since this one converges, well, the a sub n will also converge. Okay, so that is how you work on these problems. Very simple concept. Generally, if these are rational polynomials, they're fairly easy to determine what we need, because generally we want to turn it into a Betsy type situation so that we can get a number, because the number one was the best one. 0 and infinity, which were okay choices, weren't the best choices, since if it was 0, I needed that function to converge. If it was an infinity, I needed the other one to diverge. Alright, so we're back for one more problem. I think we can get at least one more on here before I have to stop this video and break it into 2 parts. So let's look at another series real quick. These generally go pretty fast, so I'm able to get 2 more in. N squared minus 10 over 4n to the 5th plus n cubed minus 2. So here's a series that we also don't know. This would have been a little bit more difficult to try to determine on your own without this test. This is not an easy one to do on your own. But what I notice is that the degree of the denominator is 3 larger than the degree of the numerator. And so that means to me that a good choice for something to compare this to is 1 over n cubed. And you'll kind of see this in a minute, and this is going to help you, I hope, become really really good experts, big experts at being able to do the limit comparison test. Okay, so let's look at this limit again as n goes to infinity. Remember, we're going to have that n squared minus 10 up there, that 4n to the 5th plus n cubed minus 2 down here on the bottom, and we're all going to be over 1 over n cubed, okay? So what this means is that n cubed is not really going to be like it's on the bottom, it's really going to be like it's multiplied by the reciprocal, and what we'll end up with is an n cubed times that n squared minus 10, which is going to turn it into an n to the 5th minus 10n cubed. And once we get there, we're at a Betsy problem, and our limit is going to be 1/4 So since we got a number, whatever this one does is the same thing that the other one does. So, excuse me. So to me, that means that this function, since this series converges, because remember it's a p-series, and that means I know that this series converges as well. So I hope that this has kind of given you a good idea of what to do when it looks like a rational polynomial. So we should probably be able to get through this one fairly quick. We're trying to pick something that's going to turn this into a Betsy. So again, here I see this one, the power in the denominator is n cubed. So I'm going to think about a series that I know. I can make mine 1 over n cubed, and that will make it to where when I do my limit, as n goes to infinity of the absolute value, it'll be 1 over n cubed minus 2, and actually I end up multiplying by the reciprocal of that, or n cubed over 1. You'll kind of get used to that as the more of you work, which is in fact a Betsy, gives me 1. Since this thing converges, that helps me know that this one also converges. Okay, the last problem I'm hoping to get to in the next 3.5 minutes is this problem of sine of 1 over n. And this problem is going to kind of bring us back to some stuff that we have done before. The problem with this one is that this is not a polynomial. This is a sine function, so we're maybe a little bit unsure where to start with it. But I'm looking at the inside of here, and I'm noticing that I see a 1 over n. So I'm going to assume that I get to kind of maybe I can compare it to that. So let's see what happens as we compare it to this function. Excuse me, the series. I keep calling them functions today. So if we look at this series, 1 over n, as we do this, this may not at first seem similar to you, but if I let something like, let's say, I don't know, w be equal to 1 over n, then I would be able to replace that with a w and that with a w. And if I thought about how when n's go to infinity, what does w do? W would go to 0, so I'd have the limit as w goes to 0 of sine of w over w. Okay, and this is just by doing a substitution of variables. So I took the 1 over n, I replaced it with w, the 1 over n, replaced it with w, and as n got to infinity, that told me what the limit was going to be as w goes to something. So what limit do I need there? And this, you should recognize, is one of your special trig limits, which is in fact 1. And so this gives me a kind of a different answer, where this thing is divergent, and since I got a finite number when I did my division, this one is also going to be divergent. Okay. So I hope that these set of 4 problems kind of gives you a really good understanding of the limit comparison test. Alright, so try to find some problems and practice them. If you have questions about this, don't be afraid to contact me on Edmodo or other means, and I'll see what I can do to help you out. Okay. Hopefully I'll be back in the class soon, and we'll get things back to normal.